I felt that it would be a good idea to before going into the problems coming from biology, and there are many of them, to have a general view of an approach that you can discuss on the free boundary problems. So before beginning the course, let me give course number 0, which is a general view. So free boundary problems have to do with models coming usually from physics, biology, where you can distinguish two zones and an interface. So let's put it like that. I will call omega of t one set. The boundary will be the omega of t. And for some reason you know that any point here on the free boundary, on the boundary, will move with a certain velocity v of xt. And this velocity can come from different origin. It can come from what happens inside the domain or outside of the domain. It can come from what happens on the surface itself. It can come from curvature, which are second order derivatives on the surface. It can come from many things. And as long as you stay with a geometric point of view, which is to describe this free surface, usually you will be faced with a problem that to describe well this velocity, you need to compute derivatives or second derivatives, and this requires smoothness of the boundary to just to compute this velocity. So you have two choices. Either you go to the direction of proving that the interface is smooth and that you can define the motion of this surface, this hypersurface, for all times because everything is well defined, or that at some point there are some singularities and then you can go further and describe the singularities. The second option, which is the option I will follow in this course, is to go to weak formulations where you try to speak of an object which is weaker than the free surface itself. And an example, the first option for that is to speak simply of the indicator function. So the first option is that you consider this function of x and t, which is defined by 1 inside the domain you are interested in, 0 outside, and now the free surface is just the discontinuity of the function f. So it's quite easy to check that the formulation of this geometrical problem in this setting will be to write that f solves a transport equation, which is d over dt f plus v of xt dot grad x f equals 0. Of course, now f being a discontinuous object, you need to know what it means that f solves this equation. And an option for that is to give a definition in the weak sense, in the usual distribution sense. And in the distribution sense, what you just do is write a weaker an equivalent formulation where you write it divergence of Vf minus f divergence V f V equals 0. And now you are in good shape because this is an object which is well defined. This is an object which is possibly well defined, and this can be well defined. So if you want to go that way, and if you want to define solutions, you just integrate by part, again the test function. So in distribution sense, you write this. and integrate by part. Again, integrate by part against a test function. So if you integrate by part against a test function that I will call g, you will get that d over dt of integral of fg minus integral of vf grad g minus integral of fg divergence v is 0. And you don't need so much information to define the solution for that. Then you can integrate in time if you want to make complete sense of this. And you see that you don't need so much sense. G being a test function which is smooth, the only thing is you need to define this object and this object. So divergence V should be in L1 at least, and VF should be well defined in L1, for example. So you need very weak information to define what is a test function. So this is a good option. The question now is how can I solve such an equation? So the usual method to do that is so we can solve the equation by the method of characteristic. Characteristics. So which means that you introduce x dot equal v of x of t and t. And here I have to follow exactly the rule I put, and I will put an index here for x and the time t, and this index only refers that at some time t0 the value is x. And what you check quite easily is that one has d over dt of f of x, x of t and t equal 0. Because when you use a chain rule, what you get here is the partial derivative in time plus x dot, which is v, partial derivative in x, which is exactly the equation up there, which is 0. So this means that the function f satisfies that f of x, x of t plus h, and t0 plus h equal f of x and t0, taking simply the times t0 and t0 plus h in this equality here, the fact that this is constant. And if you go back to this drawing, what you see is that if you take a point x0, t0 here, so now you have the velocity, what you see is that what this tells you, this should be an x0, let's say. If you take this point, after some time, this point will be moved according to that at x0 at x of t0 plus h, and so all these points will be moving according to the interface. So the function which was 1 here, 0 outside, becomes f equal 1 in this zone and f equals 0 outside. And so it's you have moved exactly according to the rule which was given here. So you just move things by transport, and that's an option. So what is the drawback of this? So this is nice because then you define weak solutions. There is a drawback to that. So the problem is the following. First of all, if you want to make it to give sense to all these computations, you need that you can solve these characteristics. So either you like the usual Cauchy-Lipschitz theory, which require that F is Lipschitz, continuous, plus control of whatever you need to control large time behavior or large effects. So you need local Lipschitz or things like that, which are usually very, very strong compared to what you want to do, because the velocity you get from real problems is much less regular than Lipschitz continuous. So this regularity is very weak. It's very strong, too demanding for what we want to do. Another option is to say, okay, but we are now in the 21st century. We know that Lipschitz continuity is too strong. We know that we can solve this kind of equations with a weaker formulation, which was initiated by Diperna and Lyons, and which only needs very weaker assumptions, and with the best assumptions due to the group around Ambrosio, what you need is still that V is at least BV. And let's say divergence V in L infinity. So you still need that the velocity, even if it doesn't need to be Lipschitz, it has at least to be BV, which means not far from W11, I mean one derivative in L1. And again, this is very, very strong compared to what we will find in practice for this velocity, at least if we want to go to weak solutions. So this approach, even though it can work, has this failure, which makes that you might want to go to a different option. So the second option I'm sorry to erase the beautiful sun on the mountains of Spain. And so that I can go to the second option. So the second option is to say that we have been a little bit too far by taking the function f, which is 1 and 0. Exactly the same argument works if you choose a function which I will call phi in place of f, and this function phi would have simply the properties that phi of xt would be strictly positive for x in omega of t, phi of xt would be equal 0 for x on the boundary, and let's say phi of xt would be negative, but you would, if you prefer to make it also strictly positive, it's fine, for x in the outside of the closure of omega. So now your function phi, which I will draw in a different color. Let's see. So this function phi would be continuous, let's say, even purely Lipschitz continuous. It will be positive here. It will be negative here. And of course, if you solve the equation, dtv plus v grad x phi equals 0, whatever you do, because of the same argument, phi will be strictly positive on this side after some time t, will be negative here, and so you can always, in the same way, define the interface now by the set where phi is 0. So that is called the level set method. Where phi equals 0. So it's better because you don't handle discontinuous function. You handle eventually continuous or even Lipschitz continuous solutions. And then you can go a little bit further and you can now say that okay, but my interface is defined by the level where phi equals 0. So the gradient phi is not anything. The gradient phi is something which points out exactly in the normal direction. Because the gradient phi in this direction, the derivative along the tangential derivative is 0 because phi is 0. So now you can say, you can observe that that the gradient phi is simply let's say grad tau phi is 0, where tau is tangential. Which means that here the velocity v, the velocity field here, is not really relevant. What is really relevant, if you want to advance the interface correctly, is not the full velocity, of course, but it's only the normal velocity. So you can describe v as, let's say, capital V times the normal plus a tangential part. And because of that, the normal is simply v grad phi divided by grad phi. This is the normal to the interface because grad phi is exactly in the direction of the normal, as long as it doesn't vanish, so that you have really a strict transition from positive to negative. So if you do that, plus v that tau, and then if you put that in this formulation, you end up with another formulation, another equation, which is now this equation for phi, which is written here, in which you say that the tangential derivative doesn't play a role and that the normal derivative is given by that. So if you put that in this relation, what you obtain finally is d over dt phi plus v of xt, which is now a vector multiplied by the norm of the gradient phi of xt, which is another option for describing this interface. The advantage of that, I mean, the first drawback of that, first of all, it becomes nonlinear. Here you had a beautiful linear equation. Here you have a beautiful linear equation. Now you have a very bad nonlinearity, which makes that you have to solve a nonlinear problem. So these linear problems comes in a class which are called Hamilton-Jacobi equation. And you would like to describe, to know exactly what we did for the transport equation, which is to know in which sense you can define solutions. And we know since the 80s that there is a convenient way to define solutions of econal equations, which are viscosity solutions. So viscosity solutions, which were introduced by Kandal and Maida in the 80s, is a convenient way to define solutions, and it has a flavor of weak solution in the distributional sense, except that rather than multiplying, what we do here, you multiply, you integrate by part, you make an additive rule. So viscosity solutions are defined as follows. If you want to make a subsolution, a viscosity subsolution, you take test functions.
Question, please, Benoit. I interrupt you because we are getting into something new, viscosity solutions. So what is the reason that you cannot do it with weak solutions? Why do you do viscosity? Just a naive question.
Well, there are two questions in your questions. The first one is why you cannot do usual distribution solutions is because it's a nonlinear object, and you cannot integrate by part and say what is the gradient phi, absolute gradient phi when phi is in LP. So this object is not well defined if you want to work with function phi which are continuous, or then if you want, so you need a gradient to do that. And
what you mean is you cannot do classical and you cannot do weak, so you do viscosity.
You can do classical, but then you will face singularities usually, so you cannot do classical. You cannot do weak because the modulus of grad phi is not well defined, because phi in principle you don't want to prove their estimates. And even if you want to estimate, you will have a problem of, if you want to define this object, you have problems of uniqueness. So you need to define the correct weak solutions in a different way.
Okay. So viscosity is the way to do this thing.
Absolutely.
Since we have to work for 6 months on this thing, it's better Sorry for the interruption.
So the definition.
Viscosity is here to stay.
So viscosity solutions are class of weak solutions.
What do you mean a class of weak solutions? It's a class of generalized solutions, but they are not weak.
They are generalized if you want.
Generalized. Thank you. Oh my God. Okay. Yeah.
So viscosity subsolution, how do you define that? You define that with the following rule. You take let psi a smooth test function. You assume, or you take functions such that the following occurs, that the maximum in x and t of phi of t of xt minus psi of xt is achieved at a certain point, right? x0 t0 minus psi of x0 t0, which is of course usual. If you take a function psi which is very large at infinity, for example, and phi here which is bounded, then if everything is continuous, so you need continuity to prove that, or at least upper semi-continuity to define this. If you can do that, which is very generic for any test function, then what you simply say that for subsolutions you write that the inequality holds true, but because you don't want to write the inequality for that, you just write the inequality that dt psi of x0 t0 plus v of x0 t0 grad psi of x0 t0 is negative. And because at the maximum point in principle the derivatives are the same, this is a good definition for a subsolution. This tells that dt phi plus v grad modulus of grad phi is negative. So this is the way we define viscosity subsolutions. For super solution, you just inverse. For the definition of super solution is simply you inverse max by mean, and you inverse inequality like that by inequality like that. So this inequality is changed, and you say you have a super solution. Okay, so this is the way they defined it. So what is the advantage compared to this thing here? So now the advantage is you only need phi and v to be continuous because you want to define things pointwise. So the only assumption you need to define this kind of object are continuity. And you don't need that the divergence v is bounded, that blah 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 v is Lipschitz or whatever, or you need much less. I will not prove that, but associated to that you have a uniqueness theory which holds more or less in this continuous regime. Uniqueness of solutions. And there are many settings of that. When you go to uniqueness, of course, you need to put assumptions, technical assumptions, which I don't want to do it here, especially because the real problems, the V depends on phi, and so we cannot touch real problems at this level. But you have a nice theory which was developed by Kandal and Lyons, sorry, which give uniqueness.
What situation V is continuous?
Sorry?
V is discontinuous with respect to
Okay, so
some distant conductivity, no?
the case, okay, let's say simple, when we have 6 months to work on that. The discontinuous cases are very, very interesting, and questions are much more complicated now. Okay, so this option is more appealing, even though the departing equation is nonlinear. You have a framework in which you can work where you don't need so much to define objects. So this is the 2 possible options. There are more of them. So I will stop here with this general introduction, and I will begin to touch real problems now. And one point of view on the course is to give problems which come from biology. Another point of view of the course is that I will give 3 examples. One example is, the first example will be where this is a natural point of view, and it comes by itself like that. The second example will be that none of them work, and there is no obvious way to put another problem in this framework. And the third example I will give is an example where this is the good point of view, and it comes naturally. I mean, this is one possible point of view, and it comes very naturally. So this will be 3 examples where you see the interest of these 2 different approaches and possibly different approaches. Okay, so this is the end of the course number 0. If there are questions, this is good time to. Yes,
All this is kind of developed with V being given.
With
velocity is given.
yes, of course.
Velocity is given. If velocity is given, all we need to do is be able to solve the ordinary differential equation.
No, but of course, what you want to do, what you have in mind, is that V will be given in terms of phi or of the omega. So.
No, I understand that.
Yeah, so it will be that's the real challenge is to couple the 2 and to have formulations which we will see one examples later on this. so now we can begin with a real example. So the first example I wanted to explain is the example of invasion fronts, which have many similarity with reaction, chemical reaction fronts. And which are named after Fischer and Kolmogorov KPP. So the problem is coming from individuals or molecules which are moving in an open media, and they are moving randomly, and they undergo reactions. Or in the case of invasion, they have a limitation due to the carrying capacity. So the Fischer KPP equation which I will rescale already to make it to that the front appears, is the following. So you consider the solution of a parabolic equation, of a very simple parabolic equation, and I put a parameter r here, which is this simple equation. So just diffusion plus a very simple reaction with a background, or in biology you have this.
After the equal sign.
That's an R.
Is this enough?
That's a rate.
Oh.
So in terms of evolution of biology, this is the rate of multiplication. It's a constant. It's the rate of multiplication when the population is free. As long as the individuals are very few, U is close to 0. This is the internal growth rate of the population. And 1 is called the carrying capacity, U epsilon. When the density of population comes close to the maximum carrying capacity, then there is no place. So food is lacking and growth is limited.
So further with audience participation, could you tell us what KPP is?
And so KPP equations is, I always forget what is the third. Kolmogorov, Priskunov, and whatever is the third name, Petrovsky, the most important one. And this is a case of a chemical reaction. So you can write exactly the same thing if you think that this is, for example, hydrogen, or if hydrogen will blow up, it will be more hyperbolic. But you think of a chemical reaction where one would be a reactant which is in infinite even big quantities, and U epsilon a small. And of course, in all the cases coming from biology or chemical reaction, you could imagine that you can make it much more complicated by writing many species or many molecules and writing systems, which can be done also with the same approach, which I will describe now. So for that you need an initial data. So we will assume that the initial data, which I call U0 epsilon, is between 0 and 1, and to be on the safe side, I'll make it strictly less than 0, and 1 and strictly larger than 0. And this is an invariant region for the PD. So whenever you fix initial data like that, U0 you cannot be negative, because at the point where U is 0, dTu will be positive because of this term. And when you reach 1, the same thing, you can only decay. So R is a constant, which R can depend on X, by the way, is given. And epsilon is simply a parameter you introduce by rescaling space and time. You see that if you take epsilon equal 1 and you decide of new scales in time and space, you can always generate this epsilon. So epsilon rescales is a rescaling in time and space. So why do you rescale space and time? Is simply because the solution to the Fisher-KPP equation looks like this. So U epsilon typically will be like this, or let's say like this. It will be smooth.
There are two possibilities. One,
Okay, let's say one example.
advancing in both directions or advancing.
Let's see if you put initially.
Maybe you put the two pictures.
Okay, if you want to do the two pictures, we can do the two pictures.
Yeah.
You want this picture too?
This is the advancing front and this is the mountain.
Yes, and so what typically what you observe is that when epsilon becomes smaller and smaller, this size here becomes of size epsilon. Okay, I should not do it like that. I should do it symmetric. I should do it like that. This size becomes smaller. And if now you look in the full space, which we will do, even though I didn't write it here. So here t is positive and x is in Rd. What you observe, so now let's do a picture in 2D. In picture in 2D, what you observe when epsilon becomes small, what you observe is that you have a front which is moving. So you have a front which, when epsilon is smooth, is quite diffused. And when epsilon becomes smaller and smaller, this front becomes sharper and moves outward. And in that case, it's with constant velocity decided by r. And if r depends on x, this will not be constant velocity. This will be driven by r. So this is what you see. And this phenomena is related to the traveling wave, that when you observe a phenomena like that, you also see that this wave is advancing with constant speed. So this wave here, you see it advancing at a certain speed. These waves here, you see them moving in this direction and this direction, so that later on you will get something like that with constant speed. In higher dimensions, this is what you observe. And in the limit, when epsilon is becoming very small, this creates this separates the space in two states, U equal 1, U equals 0. So in chemical reaction, U is 1 is a burned gas, U equals 0 is the fresh gases. In terms of ecology, these are the invasion spaces. So this is a place which is free of the invader, and this is a space which is completely colonized by the invader. So what you can, what in that case, the typical, maybe the best is to explain, is to give the outcome. So the theorem is really that when epsilon goes to 0, U epsilon of xt converges strongly to U of xt, and this function is a function which is 1 in a certain set omega t, an open set omega of t, and which is 0 in an open set which is omega o, which I call O of t, and which is well separated, which means that the complementary of the closure of omega is calligraphic O. So U of xt will converge to some function which takes values 1 and 0, 1 inside the domain which is moving and 0 outside. So this is the question: how can you prove that? So the reason why this is true mathematically now is very clear. If you take epsilon 0 here, this becomes 0, this becomes 0 which means that u1 minus u is 0, which means that u is either 1 or 0. The difficulty, of course, is to prove strong convergence, because these converge weakly only the weak sense to 0, and to prove that the sets are well defined, where you have omega, where you have 1 and 0. Those are the difficulties. So what I will present today is the approach of this by weak solutions, by Evans and Tsouganidis.
So this is a theory.
This will state it as a theorem later. Right now this is a question. How do you prove that?
So listen, question and theorem is not the same. So this is question.
How do you prove that?
And is there a theorem?
There will be a theorem, but we need to build up some theory to make a theorem. So we'll give you the theorem later, maybe.
It's very important in this 6-month period that we make the difference between question and theorem most of times. Understand? Most of the people here make a difference between theorem and question. And it's very important that we have questions. Otherwise, there is no life.
And of course, there are several approaches to that. It depends. You can use this problem by different point of view. So what I propose to do.
Another question, just this is introductory. If you prove this theorem, you will solve the problem of transport in the previous slide, in the previous question.
So this approach of Evans-Tsouganidis will be an example where the aconal equation, the Hamilton-Jacobi equation, is a perfect answer.
With this regularization?
With this problem, yes. So this will be a first example. So this will be the example, the typical example where the Hamilton-Jacobi equation, the level set method, is very well adapted. So what do they, so the approach, so the method of Evans and Tsouganidis is the following. So you assume, so the assumption on the tip, so we already made assumptions here. We'll make it more precise. We assume that u0 epsilon of x can be written as exponential minus phi 0 epsilon of x with phi 0 epsilon. So this has to be less than 1, so phi 0 epsilon is positive, right, because we need that to be less than 1, and phi 0 epsilon of x being a Lipschitz function. In fact, we'll need more, we will need a little bit more, but later we will see. So we'll need that, and I think that's it. So then the idea, okay, and phi 0 is positive, and Lipschitz, and so now what you see is that, what is the purpose of this? Why do you do that? Is that now what you see is that u equals 0 corresponds well to the place u equals 0 is more or less, it's not completely obvious, it's more or less a set where the limit, where phi 0, which is the limit of phi 0 epsilon, no, okay, we have also, you assume that phi 0 epsilon converge to phi0 locally uniformly, because it's Lipschitz continuous locally uniformly. So this limit is strictly positive. Because when phi0 is strictly positive, you see that this is exponentially small. I forgot the epsilon here, which is of course the most important point in this construction, is that you assume an exponential decay. So where phi0 is strictly positive, then u is exponentially small. So this set where u equals 0, which is here, becomes more or less the set where phi0 is the open set where phi0 is positive. Of course, it's not completely true. One is open, one is closed, but we see that as a connection. And when phi0 equals 0, this, again, this is not absolutely clear either, but this is more or less 0, so you expect that u equal 1. U0. Which of course you can enforce when you choose initial data. So you distinguish now a zone where phi is really small and a zone where phi is where u is very small, which means phi is positive, and a zone where u0 is 1 and phi is 0. Yes. Initial data. That's the initial data. U0 is just. And of course, what you would like to prove is that this is true for all time. So you write for all times u epsilon of xt equal exponential minus phi epsilon of xt over epsilon. And you expect that this is true for all time, and that rather than solving this problem, where u is not very smooth, you can solve the similar problems on phi, where you get now something which seems to be simpler. So the first to explain the reason why this is an option, let's do a little bit of algebra about the derivatives of this object. So if you compute the x derivative of u, you will get minus dx phi over epsilon multiplied by u. Epsilon, phi epsilon, u epsilon. If you differentiate twice, what you will get is minus d2xx phi epsilon over epsilon u plus dx phi epsilon squared over epsilon squared u epsilon. So now if you rewrite the equation which is here on phi, what we obtain is simply that, so x derivative or time derivative is the same, so you will get, so now we have to multiply by epsilon, this epsilon goes away, we have to change signs, so this is the most difficult part of the proof, is to get the correct signs at the end. So that I hope you will help me if I make mistakes. So this is the first term. This one you multiply by epsilon squared and you change sign. So the minus becomes plus, so you get a plus grad phi epsilon squared. This term stays with a minus and is multiplied by epsilon squared. This gives you minus epsilon Laplace phi epsilon. And on the right hand side, the u epsilon factor out everywhere, and you change sign, so you should get something like that. So I think it's better to check. So this is correct. This is correct. And in this new problem, you see that when you were passing the limit in this problem, the only answer you would get is this one. If you pass to the limit formally in this problem, then in the limit we expect you can pass the limit and you get dt phi plus grad phi squared equal minus r 1 minus u, which is not a very nice setting. You see that there are difficulties. This is certainly not very interesting because you cannot be easily connected to phi when because this argument now up there that u equals 0 when phi is strictly positive is certainly correct, but what is not obvious at all is that when phi epsilon converges to 0, that u epsilon converges to 1, because phi could be of order, let's say, epsilon, converge to 0, but exponential phi over epsilon could be non-zero. So this, how to connect this to phi is not at all obvious. How to relate this to phi is a real question. So let me give you the theorem and maybe we'll continue this afternoon to prove to see how you can prove that. So the theorem we will prove is the following. So the assumptions are there. The first statement is phi epsilon is uniformly Lipschitz. The second statement is that phi epsilon converge to certain phi locally uniformly. Just a consequence of Ascoli-Arzela theorem. And the third statement is phi is the unique solution, the unique viscosity solution of the equation mean of dt phi plus grad phi squared plus r, and phi is 0. Okay, so the first, so this is what we will prove this afternoon. Let me comment about that. So the fact that phi epsilon is uniformly Lipschitz is a very standard idea on Hamilton-Jacobi equation and gives the interest of changing from u to phi. So u is a not very nice function, it's a discontinuous function. Phi is Lipschitz. That is much easier to work with Lipschitz functions than with discontinuous functions. We all prefer that. So this is the first advantage, and this is the usual philosophy on parabolic equations with small parameters. Usually the solution is not good, the log of the solution is much better, and phi is the log of u multiplied by something. So that's something. This thing, there is no need to comment it. That's simply a consequence of that. Except when epsilon converges to 0, the only comment is that the full family will converge because of uniqueness. So you had, of course, the proof will go in 2 steps. First, you extract subsequences, but afterwards you end up that there is a unique solution of this equation. So you know by uniqueness. Of course, you need an initial data, which is given by the assumptions which were done up there. So you find afterwards that the full sequence converge. So in the interest, and in 5 minutes I can explain why this is true, why this equation is not very good, but why this one holds true. So what is the reason of that? The reason for free is simply that the fact that the mean is zero. What does it mean? That means that that phi. So it means that phi is non-negative, which we already know because phi epsilon is non-negative because u is less than 1. So we already know that. Is that dt phi plus grad phi squared is larger than minus r because plus r is positive, but so this is larger than minus r, and this is quite obvious because u is positive, so this object is certainly larger than minus r, so this is okay. So this one is okay, this one is okay, and what is the next meaning is that if phi is 0, of course the mean is 0 because both of them are 0. So if phi is strictly positive, so where phi of xt is strictly positive, what you know is that u epsilon, which is the exponential minus phi, is certainly 0. So u epsilon converges to 0 at this point xt. But this is true in an open set because phi is Lipschitz continuous. So in an open set around this point, u epsilon converges strongly to 0. And because u converges to 0, this u is 0, and you can write that dt phi plus grad phi squared equal minus r. So you get the equation. So you get exactly this information here. Okay? So because of that, now you have a complete description of the function phi epsilon. So I will stop here for this morning. What remains to do are two things. Just show that these statements are true. So this statement has to be explained in the viscosity sense. And the second thing is to explain how you pass from this theorem on the right to this statement. And of course, there is a big difference. When phi is strictly positive, that's clear that you converge to 0. The difficulty is this set. Is it true that when phi equals 0, is it true that you converge to 1? And this is not at all obvious. Because again, phi could be over the epsilon, which means that exponential phi over epsilon could converge to anything but 1. So there is something more to work, which is very interesting, and which is here. And there are many, many questions which are still open in this point of view, which I will explain tomorrow, this afternoon also, to conclude the course. Thank you for your attention. And of course, during the coffee break, I'm ready for any question.
Some questions?
Where do you recover the velocity from this equation?
Okay, correct. So what is a real? Okay, so I said this is a beautiful example. So So there are two things. First of all, it's not exactly the econal equation because you have that, and because even when you say we have cut the two we didn't put a negative part outside the zone, so let's forget about that. This mean comes from the fact that you have put 0 on the right. The velocity will come down from the r now, not from this term exactly. So it's not exactly, you are correct, it's not exactly compatible with the explanation of the velocity which was here. The velocity comes from that, but this is a change of variable. You can see it as a change of variable, or it's like in geometrical optics, there is something similar if you speak of time or potentials.
In fact, there is a question before, maybe, which is that this equation has compact support, right?
If you put it initially, yes. If you put initially compact support.
This is why you get a free boundary, because this has compactly supported solutions, right? So this is something that you have to prove also.
Yes, so what you have to prove,
So
yes, more or less, this is not proved.
Equation.
Yeah.
Yeah. But yeah.
And then once the free boundary is there, there is the question of what is the velocity of this free boundary.
Yeah.
So there are two questions to discuss this afternoon.
Yeah.
More questions? Okay. So let's go for coffee. Thanks.